Well, say hello to everyone. Thanks for coming for the special class today. When the other people are watching this, I will be eating good Chinese food, I hope. So the last class, I had this little question here for you. And after class, it was clear that there were a lot more questions on this. So I thought I'd come back and see if I can do a better job of explaining what's happening here. So we're getting this interferogram here. And the fringes are basically straight. But there's a region here where there's a little bend in the fringes. And the question is, does that correspond to a high spot, a hill on here, or is it a low spot, a valley? And just by looking at this interferogram, there's no way we can tell, because we don't know the sign of the wedge or the tilt in the system. But we're going to get one additional piece of information, and then we'll be able to solve whether that's a high point or a low point. And the other piece of information, oops, I didn't mean to do that. The other piece of information I wanted here is that when I push in on this mirror, the fringes are going to move towards the right. Now, I think one thing that was confusing people is that when I push in on this mirror, the thought was, well, I'm changing the radius of curvature of the beam that's coming back. And I guess that's true to a certain extent, but we're not going to push in very much. We're going to push in here half a wave or a wave, something like that, just to cause the fringes to move us maybe one fringe spacing or so. So that would be pushing in a half of a wave. And so while the curvature is changing here, and when I push in, then the fringes may not be quite as straight. The change is actually very, very small, and that's not what we're going to be seeing. We're not going to be seeing the curvature come into the fringes because we're not pushing enough, but what we're going to see is just a motion of the fringes here. They're going to move either to the left or they're going to move to the right. And when I push in on this, and as I said, I probably won't even use my finger. I might just put a little card up against it, or maybe just hold on a piece of paper and have that touch it. It's just barely moving it. Let's say the fringes move towards the right. Now, my simple-minded way of thinking about that is that when I'm pushing in on it, I'm actually causing a bump over the whole surface. And a bump over the whole surface caused the fringes to move this way. And so in this particular region here, this corresponds to just a little localized bump. Now, if I had tilted the mirrors the opposite direction, everything would have changed sign. In that case, if I had tilted the other way, the fringes would not have come like this, but they would have moved the opposite direction. And now pushing in on this would have caused the fringes to move the opposite way. And maybe the best way for seeing that is to go back several slides here. So just hold on. We'll go back a few slides to here. And let's look at this case where we had the Fizeau here. And we said, well, along a given fringe, the separation between the two surfaces is a constant. Okay? And now, we put in enough tilt here, so we didn't have any closed fringes here. We had open fringes. And what that means then is that I put in enough tilt that as I move from left to right across here, the separation between the two surfaces is always increasing. And so we said here, as we come along this bump, the fringes are going to have to move towards the open portion of the wedge. And so the fringes look like this. Now, if I were to take this whole thing and move it up and down a little bit, we know that for a given fringe, the separation between the two surfaces is a constant. So if some way, if I were to move the reference up to make the separation a little bit more, the fringes would move which direction here? They'd have to move towards the left. Because along that fringe, it's a constant separation. So if I were to increase the separation, that fringe would have to move in this direction here. If I were to push these closer together, if they were not really touching, and if I were to push them closer together, then these fringes would move towards the right. Because again, along that fringe, it's a constant OPD, and if I were to decrease this separation here, this would have to move in a direction to keep the separation a constant, so it'd have to move towards the right. And if I were to put the tilt the opposite direction, well, then the fringes would have moved the opposite direction, and then the motion of the fringes, due to either increasing or decreasing the separation between the two surfaces, would be just the opposite of what we said before. So I don't know, does that make it any clearer, or is it still puzzling? Getting the sign is always a difficult thing to do, determining whether it's a bump or a valley. Okay. So I think maybe it's easier to think about this way, where we can actually see the two surfaces and we see a little wedge between them, and we can kind of figure out if I were to increase the separation between them, the fringes would move towards the left. If I were to decrease the separation, fringes would move towards the right, and so on. And so this is really equivalent to what we talked about in the last class of this one here. Any questions? Okay. I'll have to have a little drink then. Well, as I was saying earlier, this is also always very puzzling, and I've seen a lot of people who really know optics very well to have this wrong, thinking it's a valley when it's a hill and vice versa. Okay, so the next thing we had talked about last class, we mentioned the Mach-Zehnder, and I have found the Mach-Zehnder to be a very, very useful interferometer for me, but not quite the way as shown here. Where I found it useful is in this modified Mach-Zehnder here, where I've put a telescope in both arms here. So two lenses separated by the sum of the focal lengths. So we have collimated light going in, light coming to focus, and then collimated again. And the same thing up above. So we have two collimated beams coming up. Now, the one difference between the upper leg and the lower leg is that up here, I've put a pinhole at the focus. And I'm going to make that a very small pinhole. That is maybe half the diameter of the airy disk that we get when we bring this light to focus there. So the purpose of this interferometer is to measure the shape of the beam coming into it. So this may be some complex optical system here. Where I have used this most was for testing of the wavefront quality from a laser diode. So we'd have a laser diode here, and we have maybe some optics in the output. Laser diodes often have astigmatism in the beam, and so you put in some optics to try to clean out the up the astigmatism. And so the goal here probably was to have a nice collimated beam right here. Well, how good of a collimated beam is it? Well, this instrument here can tell us, because we'll send the beam in. Up here, we have some aberrations in this beam. Up here, the beam is focused on this pinhole, and if this pinhole is small enough, it's sort of like half the airy disk diameter or smaller, it will clean up the aberrations in the beam. And so after the pinhole, I have a nice spherical wave, and that would be collimated here. So this will be my reference, and then that will interfere with the test beam, which comes along the bottom. And so the fringes here are going to tell me the quality of the beam coming out of the source. Okay. So back in the days when I was running WICO, we had an instrument called Ladeite, and Ladeite stood for something like laser diode tester. And it really was like this, except we used phase shifting, which we'll get to in another class or two. But we sold quite a number of these for testing the quality of diode lasers. But it could be for testing the quality of any type of optical system. We just take the beam coming out, send it into this modified Mach-Zehnder. Now, I put two telescopes here, and I probably could build this without a second telescope down here. But the telescopes here flip over the beam, and so we always thought it was good to flip over the beam down here. Plus, the real reason, maybe the more important reason, was that these sources that we were testing often did not have a very long coherence length. And so you really wanted to match the paths here. And if I had just glass in one and no glass down here, then I would have some dispersion up here. And probably the contrast of the fringes would not be as good as if I put the same amount of dispersion down here to make the two paths, the optical path lengths for the two arms, almost exactly the same. So this is what I think is a very good use of a Mach-Zehnder type interferometer for testing the quality of a beam going into it. Later we'll talk about another interferometer called the smart point diffraction interferometer. It does the same thing, but either one can be used. Any questions on that? Okay. So what we have next in the notes will be a bunch of interferograms. And I want to go through here and just say a few words about all of them. And of course I'm going to start here with my favorite aberration, spherical aberration. But before I do that, I have to tell a little story here that tells you a little bit how computers have changed. When I came out here I joined the faculty in 1974, and I found out that Roland Schack had just recently put together a set of interferograms that looked something like this. His were binary, these are more gray level, but they looked a lot like this. But it was a great set, very, very useful. And the thing about, this is 74, we didn't have personal computers like that. So he had used what was basically an HP calculator, which was much, much bigger than my notebook computer here, and much less powerful probably than my iPhone is. And for him to draw, and connected to this HP calculator, he had a plotter that had a pen writing on paper. And for him to do one of these interferograms would take all night. And so he was so proud, and he should have been. He was so proud of having this very nice set of collection of interferograms. And they have been published many places. You'll see them. Malakara has them, and in his book, and there are many places that people have copied the interferograms that Roland Schack made. Of course, now to do this, do it on a computer takes a small fraction of a second. And so these are not the same interferograms that Roland drew, but they're certainly very similar. So the first one here is, first column here, is no aberration, no spherical. And it simply is some defocus. So this would be like for using a Twyman Green interferometer for testing a spherical mirror. And we're changing the the distance between the diverger lens and the spherical mirror. So when I get it just right, the beam coming back is collimated, and we get these beautiful, straight, equally spaced fringes. Now, if I change the separation just a little bit between the diverger lens and the sphere, the beam coming back will be slightly curved, a little bit of curvature, and we often say a little bit of defocus, and so the fringes will be curved like this. And I guess what we've done in going from here to here is that we have one of these is where the distance between the lens and the spherical mirror is too large, and then the other one is where it's too small. And right in the center where it's just right. So that's with no aberration. Then the next two columns we have some spherical aberration. And I think I'll go right to the right column because that has a lot of spherical, so that's maybe more interesting. If I go up here to the top one that we call paraxial focus, we see here that in the center we have straight fringes. So this might be for like testing a parabolic mirror at the center of curvature. So we're going to get a little spherical aberration. So we first set it up so that the focus of a diverger lens is at the center of curvature of the center portion of the mirror. And so the fringes in the center here are pretty straight and equally spaced. And then as we move out from the center, well, we see a lot of curvature in the fringes. That's rho to the fourth term, the spherical aberration term. We see that. And I guess we put in a little tilt here. That's why we have the fringes across here, a little horizontal tilt. Now, if I change the separation between the mirror and the diverger lens, I might get something like that. And that's where, for this region right here, where the fringes, they go out and then they turn back. So that's where now the center of curvature of this portion of the mirror is at the focus of the diverger lens. So simply taking spherical and adding to it, or subtracting from it, maybe you want to say, some defocus. And then what we have down here is where now it's just beginning a turnaround at the edge here. And so this is where the center of curvature of this portion of the mirror is at the focus of the diverger lens. So all three of these in this column here are for testing a mirror having the same amount of spherical aberration, and the only difference is that we've added or subtracted a certain amount of defocus here from the spherical, and that changes the shape of the fringes. Okay. Now the next one we're going to look at is astigmatism. And so here we have 8 interferograms, and they're all for the same amount of astigmatism, but a different amount of tilt. So here we're putting tilt in the horizontal direction, one way or the other way, tilt in a vertical direction, and at plus or minus 45 degrees. So this is where we have put, we're at sagittal focus. So you can think of, again, with a diverger lens, we might be testing something with a little curvature with some astigmatism in it. And so our focus of our diverger lens is at one of the line foci. Because you see here, the fringes are straight here and here, but they're not equally spaced. The aberration is going as rho squared, or I should say as y squared. And so fringes are straight but not equally spaced. If we look here, well, that's kind of interesting. Now the fringes are equally spaced, but they're not straight. So we have essentially a plane wave in this direction and a cylinder wave in this direction. So I think that's kind of nice. So that's without too much astigmatism. You see this region here is probably the same as that region there. So it's just as we change the tilt in one direction or the other direction, the wider space fringe is going to move up or down. Now the wider space fringe is where the tilts of the two beams are about the same. And so, you know, it's a cylinder, and we're matching a cylinder or trying to match it with a plane wave. And so this is where we do the best matching, and then as we move away from there, it gets worse and worse. The angle between the two beams become larger. So this is for a small amount of astigmatism. Now we'll put in more astigmatism, and we get something like this. It's the same basic idea. So here fringes are straight, but not equally spaced. And here, maybe it's a little hard to tell, but they're actually equally spaced along here, but certainly not straight. And so this was tilt in this direction, this is tilt in this direction. If I looked at the one in the middle, which I don't have in here, but we'll see one in a minute like that. If I looked at the one in the middle here, it would kind of look like this, but this wide region here would be centered on here. So it's a cylinder, and it's, you know, the wide region is where the two wavefronts match the best they can. Okay. So that's at sagittal focus. So that's at one of the line foci. If I go right in between sagittal focus and tangential focus, I have what we call medial focus. And what we have here is a wavefront that is like a saddle. No, it's concave in one direction, or convex in one direction, and concave in the orthogonal direction. And what we get is a pattern that looks like this as I change the tilt in the y direction, or if I change the tilt in the x direction, or plus or minus 45 degrees. And if I had the one in the middle, which I don't have on this slide, I think we'd see one in a little bit, it'd be just like this, but this would then be centered in this. So again, this is where the reference matches the wavefront the best of any place here. So that's kind of neat, kind of cute. So we've had spherical, we had astigmatism, now we need to do coma. So this is now looking at coma. So coma, remember, that's a cubic curve, not rotationally symmetric, but cubic curve. And so we get, if we have no tilt, we get something like this. And if I introduce tilt in a horizontal direction, I get these fringes that look kind of S-shaped. You always see S-shaped fringes with coma. And then if I change the tilt in this direction, well, remember that it's kind of a cubic thing. And this is where my plane wave is matching that the best possible, I guess, or slicing through it, maybe I should say. And then this is in the opposite direction. So the fringes get closer and closer together. So this is kind of interesting in that we have an order number here, and we have the same order number, same fringe comes way out here. Okay. So that would be for coma. Now let's look at one here with spherical, coma, and astigmatism on the same plot here. And so what we're doing now is we're changing the focus. So if I'm testing a mirror, just changing the distance between the diverger lens and the mirror that I'm testing. And top one is spherical. So I guess the first one here is where we're at paraxial focus. So we get widely spaced fringes in the center. Remember, this goes as rho to the fourth. So in the center, things don't happen very fast. Okay? And then as we get out towards the edge, it happens much faster. Now we're going to introduce a little defocus here. And so now I have a rho to the fourth minus a rho squared term. And so we're subtracting the two. And here's where you have the wide zone is where they the slopes equalize one another. And then if I keep going in the if I keep adding defocus, I may get something that will look like this here. So this is kind of interesting, what happens as I change the focus term with spherical. It's not nearly as interesting with coma as I change focus. Just not very exciting. Astigmatism becomes exciting again. And so here's the medial focus. So this is where we'd have our saddle-shaped, concave in one direction, convex in the other. And if I add a little curvature, I can tend to make this wider spaced here and becomes closer spaced there. Or maybe it become clearer as I go in the other direction here. As I go in the other direction, instead of being wider spaced in the vertical, it's going to become wider in the horizontal. And then I keep adding in defocus until I get to my line foci. And now I get straight fringes, but not equally spaced. And if I kept going in this direction, kept going more, then I would get this over here, but rotated 90 degrees. And then if I keep going, adding in more curvature here, then I'll get ellipses like this. Okay. So all of these, these at the bottom are all for testing the same wavefront, but adding in a different amount of defocus. Now, if you go to my website, I have that Fun with Mathematica section up there, which I've shown you before, where you can go in and you can quite quickly calculate all these patterns and play with different amounts of aberration and defocus and so on, tilts. The last slide I have on this is showing combining different aberrations. So this is a pattern for spherical with a certain amount of defocus. And this is, again, our pattern for coma that we've seen. And this is our pattern for astigmatism. And, you already, just looking at these, you know right away what the aberrations are there. Now we combine spherical and coma, and we get something like that. Or spherical and astigmatism, we get something like this. Or coma and astigmatism, and we get something like this. So it begins to get complicated pretty fast. And then just for the heck of it, we combine all three, and it becomes a complete mess. So even though you're going to become very good at recognizing the Sagittal aberrations, as you begin to mix them, it's very easy to get confused. And I think this really illustrates to you the importance of having some type of computer analysis here so you can tell just what the aberrations are. Okay. So after a while, everything you look at, you're going to see interferograms in it anymore. So kind of neat. So any questions? Okay. Well, we're kind of aiming towards the computer analysis of interferograms. But before we get there, I want to talk a little bit about Moiré patterns, interferograms. I don't know, I've been fascinated with Moiré patterns for many, many years. And I have to tell you, I love to go on Google and just search for the word Moiré, or search for the word optical illusion. You get, under optical illusion, you get a lot of Moiré patterns too. And there's some beautiful things out there on the web. A lot of them, they show movies up on YouTube. It's just, you can waste hours just playing with seeing what there is up on the web. Now, I don't want you to waste hours. I want you to be thinking about how these Moiré patterns are connected to interferograms. But I tell you, it's a lot of fun to see them. So what I want to do here I mean, very early in my career, I realized, that interferograms and Moiré patterns can look pretty much the same. And there's probably some relationship between the two. And in going through a little bit of math, which we'll do in just a minute, we're going to see that Moiré is really a very useful technique for aiding in the understanding of interferometry. And I just start off here by showing where we put together two patterns, which are just straight line patterns, and we superimpose these and rotate one relative to the other one, so we have an angle of 2 alpha here between the two patterns. And I look here and I say, oh, that looks like interference fringes to me. I see here these dark lines, and that's when these two patterns are out of phase. So it's sort of like destructive interference for interferometry. And then I see this bright region here, and that's where the two patterns are in phase. So that's sort of like constructive interference. And then I can measure the separation between the two, between two destructive interference regions or two constructive interference regions. And I end up with something that this separation turns out to be whatever the grating period is divided by 2 sine of alpha. So then I kind of think back to the interference of two plane waves, and I realize that if this grating period is equal, you think of that as the wavelength of the two plane waves, and I can say, well, this is 2 alpha is the angle between the two plane waves, and I get this fringe separation here, which is the same as the interference fringes that I get. The grating period, the wavelength divided by 2 sine alpha. So that's pretty interesting. So let's go through some math and see just how that works. And we wrote some stuff up in chapter 16 of Malakara's book. And so what I'm going to go through here is part of what we put in chapter 16 of Malakara's book. So when I think of these Moiré patterns, what I'm really doing, I'm taking two sets of patterns, I'm putting them against each other, and I'm looking at the overall transmission. So it's like the transmission, this time I'll say intensity transmission, of one pattern times the other pattern. So I'm seeing the product of the intensity of the two intensity transmissions. And that's all you need to know to go through the rest. That I'm seeing a product here of the transmission function for the two patterns. So let's say that the two gratings have a transmission function. I'm just going to say, well, one is F1, that's a function of position x and y, and the other one is F2. And I don't know what these patterns are, but I'm going to write it here just as a bunch of cosines. And I'm going to put in a little constant term in front, because these are intensity transmissions, so it can't go negative. So I have to have something in front here. And it's a cosine of, well, n phi of x and y, n phi 1. So phi is the function describing the basic shape of the lines, whether they're straight lines or circular or whatever. And B's are coefficients that really determine the profile of the lines. So back here what I had was just binary lines, but it doesn't have to be binary lines. But it could be sinusoidal, it could be whatever, but that's determined by the B's. And the phi's here determine the basic shape of the lines. And so when we put these two gratings together, we're going to see an intensity function that's given by the product of these two. So we're going to multiply one times the other here, and we're going to get a mess. It looks horrible up here. And so we have a mess of, well, we have the constant terms. We have something that goes as cosine m phi 2. So this is like the basic lines that I started with. And then we have something cosine of n phi 1. So this are the basic lines that we had before for the other pattern. And then we get this term here that's even a bigger mess, but it's more interesting. It's going to be a summation of the cosine of phi 1 and the cosines of phi 2. Well, I'm just going to look at this last term. I'm going to say, well, these first terms, you know, this is going to give me some DC level. This is going to give me something that looks like the two patterns. And then this is going to be the interesting term, this product of the two cosines. So I can rewrite that. And when you do go up to a trig identity, you look at the product of two cosines, you're going to get something that goes as a cosine of the difference and something that goes as a cosine of the sum. So that's what I'm writing down here. So I have first line is a cosine of the differences. So here, you know, it's like cosine of n phi 1 minus m phi 2, and we're summing that over the n's and the m's. And then down here is something that's the sum of the two, n phi 1 and m phi 2. But this first line then is just, it's something that's giving us the difference between the two gratings. And I'm splitting this into two parts. I have this summation over everything, and I'm taking out of that the terms when both n and m are equal to 1. So this is where n and m are equal to 1. So I have phi 1 minus phi 2, and this is where they're not equal to 1. So the first term is giving me the difference between the fundamental pattern making up the two gratings. So that's kind of interesting. Let's say that the lines we have straight lines for the first thing here. And let's say we have two gratings, straight lines, where the line spacing for the two gratings will be the same. We'll call it lambda. It has an angle of 2 alpha between them. So one of these functions I could write as 2 pi over lambda x cosine theta plus y sine theta. So it's tilde some angle. I said theta, but alpha, x cosine alpha plus y sine alpha. So it's just straight lines tilted an angle alpha. And the second one is the same thing, same spacing lambda, but the tilt's in the opposite direction. Alpha becomes minus alpha. So I have x cosine alpha minus y sine alpha. And then I go back here, so what I'm seeing is the cosine of the difference between these two. And so that's going to be a maxima when that difference is some integer times 2 pi. So I just subtract these two and set it equal to m times 2 pi. And it tells me that these fringe centers are given by m lambda is 2y sine alpha. That's the same result as you got in 505, if you remember back, when I interfered two plane waves, tilted an angle 2 alpha with respect to each other. So it's this here, which is this term right here, that is giving me these light and dark lines here. The other structure you see here, which I'm going to try to ignore, is coming from these other terms. You have just individual frequencies, and then you have the sum frequencies. And what we're really interested in is just the low frequency term. So we're kind of filter out the high frequency stuff and see just the low frequency term. And that low frequency term is just the same as what we got when we interfered two plane waves. So you can think of this thing on the left here. That's just a plane wave where these lines are separated by the wavelength. And when we superimpose these two plane waves, we get these interference patterns. And in the Moiré, we get kind of high frequency noise too. But if I just look at the low frequency, it's giving me the same thing as the interference patterns. So isn't that kind of neat? Well, plane waves are fairly simple, but this also works for other types of patterns. And so I just happened to bring a spherical wave with me today. So here's my spherical wave, upper left here. Now why do I say that's a spherical wave? Well, I look in the center, and that's sort of like the point source here. And then these waves are coming out from there. And these waves are all, they're separated by, you know, these circular rings are separated by the wavelength of light. So I've kind of taken this plane wave and I've just frozen it in time. Okay? So that's my plane wave. Now what I'm going to do, I'm going to interfere, that's not my plane wave, that's my spherical wave, excuse me. I'm going to interfere this spherical wave with itself, but translate it a little bit from one another. And so here I have 2 point sources. Okay. So these are the 2 spherical waves. And when I interfere 2 spherical waves, what's the shape of fringes I get? In 505, I remember it's always hyperbolas. Okay. I mean, the hyperbolas may look like straight lines if you go out far enough, but they're basically hyperbolas. And if I went through all the math here, just the previous calculation from here, I would show that these are the hyperbolas. These are my interference fringes. So now if I look over here in a plane perpendicular to the screen, where I say plane B is, what I'm going to see will be basically, well, they're not exactly straight, equally spaced, but they're pretty close to that. So in plane B, I would say see straight, equally spaced fringes. And lo and behold, I mean, that's sort of what I see here. These are, they're equally spaced. And if I go in and out of the screen, they're going to be basically straight. So these are the fringes I'd see in this plane. If I look up in this plane up here, so these 2 point sources are separated in the y direction. If I look up here, well, because of symmetry, I think for a second, because of symmetry, so the 2 point sources are along a line here. Because of symmetry, if I look in a plane here perpendicular to the screen, these fringes have to be circular because of symmetry. And in the center here, the angles between the 2 beams is pretty small, so the fringes are going to be widely spaced in the center. And as I move out from the center, the fringes are going to get closer and closer together. And so in plane A, it turns out this is the shape of the fringes that I would see. Okay? So this is all pretty exciting, I think. And in 505, I'm sure you saw this when you interfered spherical waves. Furthermore, if I think about this pattern here, if I just think here for a second, and I say I put a plane right here, these could be thought of as a point source right there. These could be thought of as lines of constant, well, could be lines of constant phase here in a plane perpendicular here. So I could think of, if I take 2 patterns like this and find the moire between them, that would be like interfering 2 spherical waves. It's sort of like looking in this plane right here. And lo and behold, if I take 2 patterns like this and find the moire between them, lo and behold, it becomes straight fringes. And as I separate these sources, separate the two patterns, the fringes are going to get closer and closer together. And I'll give a demo of that in a little bit. Okay. So that's pretty, I think that's pretty interesting. Somehow, I wouldn't have guessed that the moiré of this with itself, separated, will give me straight lines, but it does. Okay. Then I could go on here and I could say, here I have what is tilt fringes. These are straight, equally spaced fringes. And then this is, so this is 20 fringes of tilt, I guess, across the radius here. This is 20 fringes of tilt across the radius plus 4 waves of defocus. And I'm going to show this live in just a little bit. But if I find the moiré between here and here, I'm going to get a pattern like this. And now if I rotate one pattern relative to the other one, that's sort of like changing the tilt between the two beams. So this one is taking the tilt out of this pattern. So I'm getting these circular patterns. This is just my 4 waves of defocus. 1, 2, 3, and 1 at the edge is 4. This is now tilting one relative to the other ones. So that's like introducing a little tilt. Again, you can go back and go through the math and see if that's the case, but it's like introducing a little tilt. And so that's taking my spherical wave and introducing a little tilt. The fringes look like that. Moving on. So what I'm going to do is I'm going to take this tilt pattern, which is 20 waves of tilt across a radius. I'm going to find the moiré between that and this pattern here, which is 22 waves of tilt, 4 waves of spherical, and minus 2 waves of defocus. So that has 22 tilt. Here I had 20 tilt, so I won't take out all the tilt. I'm going to get something like this. So there's still a little bit of tilt left, and it's 4 waves of spherical minus 2 waves of defocus plus my 2 waves of tilt. Here I have 20 waves of tilt, 5 waves of coma, and so if I moiré that with my 20 waves of tilt pattern, I'm going to get this. Or this one is 20 waves of tilt, 7 waves of astigmatism, minus 3.5 waves of defocus. I will moiré that with 20 of tilt, and my tilt will go away, and I'm left with 3 waves of astigmatism, minus 3.5 waves of defocus. And so it's going to be a saddle shape here. That's kind of neat. Now here I have 2 identical patterns, and I think it was the one right here, the 22 waves of tilt, 4 spherical, and minus 2 defocus. I take these 2 patterns, I put them on top of one another, and I rotate one slightly. So I'm finding the difference between this and itself rotated a little bit. So the spherical and defocus will subtract out, and I'm just going to be left with some tilt caused by the rotation. And that's what I get here, some tilt caused by the rotation. Then I take these 2, this one and an identical one, and I flip it over. So when I'm flipping it over, I'm changing the sign. So I'm changing the sign of the spherical and sign of the defocus and sign of the tilt. So what's going to happen here is that tilt's going to subtract out, and I'm really seeing the difference of the difference. So I'm getting the sum here and getting just the spherical and the defocus. That's kind of neat. the last one here is I'm going to take the pattern with 22 waves of tilt, 4 spherical, -2 of defocus, and I'm just going to translate one relative to the other one. So I just do a little vertical translation. Now, we haven't talked about shearing interferometers, but later in the course we will. And this is going to be like a shearing interferometer. So I'm taking the wavefront, I'm finding the difference between that wavefront and the identical wavefront, except that they are shifted a small distance. And it turns out this is the pattern, the lateral shear interferogram I would get. And that looks like coma. Well, what I had down here was spherical and defocus. But when I'm doing a shear, I'm seeing something like the derivative. And the coma would be the derivative of the spherical. And then this is shear plus a little rotation. So it's shearing and then adding in a little tilt. Down at the bottom, we have horizontal shear. And then horizontal shear plus rotation. So again, it's finding a slope, and then adding a little tilt. So can I convince you that this is a great way to think about, that Moiré patterns is a great way to think about interferograms? Now one last slide and then we're going to play. I'm going to get out my iPad and play with the iPad. So Moiré patterns are produced by multiplying the two patterns. Not addition, it's multiplication. And if we were to do addition, it would be a different story. Because when we did this multiplication, remember we got the difference and the sum. We got the phi1 minus phi2, and we got a phi1 plus phi2. It's the difference we're looking at. And if I, and I got that by multiplying. If I didn't multiply, if I just added, I don't get that difference term. And so if I were to just set up some system where I saw the two patterns, where I added the patterns, I would not see the Moiré patterns. Now, if you try that, it turns out sometimes you do see the two, sometimes you do see a Moiré pattern. And what could that come from? And that's because your eye is a nonlinear detector. And so when you do the nonlinear detection, you introduce terms that are proportional to the product of the two intensity functions. So in this case, you have to resolve the individual frequencies. When you're doing the difference, you don't have to involve the individual frequencies. You just have to be able to resolve the difference between the two. So any questions on Moiré before I play here for a second? Okay. Well, we'll try playing here, see if this works. To do this, I have to disconnect my computer, and I have to connect my iPad. I could do it on the computer, but it's actually, it's nicer, more fun to do it on the iPad here. So this is two spherical waves. So you see the beat. So what I used to do for years, I had these patterns and I set up an overhead projector and I would play with the patterns. But now I don't want to use that old-fashioned overhead projector. And so I was thinking actually for years, I hate to say this, how long it took me to do this. And I finally realized I knew I can draw these patterns. I've been drawing them for as long as we had computers. But to be able to demonstrate this on the computer, what I had to do was to make these white lines transparent. And I finally realized, you can do that in Photoshop. So I just I used Mathematica to draw the patterns, went into Photoshop, did whatever you have to do to make these transparent, and so now this shows it up pretty nicely. You can do it on the computer. Okay, so you can see here that, as the point sources get further apart, the fringes get closer together. So I get them closer together, of course the fringes become more widely spaced. So that's okay. So that's for these spherical waves. Now we're going to interfere two spherical waves. So I have 2-point sources here, and then I'm going to look at so I have a line connecting these 2-point sources, and then I'm going to look in some plane that's perpendicular. Well, the perpendicular to this plane is going to be perpendicular to the line between the 2 points. So let me come back here. I'm going to look basically at the top or the bottom here, at the fringes. And so that's these patterns here. So again, you can see how as the point sources get further apart, the fringes get closer together. And then we have, just straight lines here. So that's interference of two plane waves. And now I should be able to change the angle between the two plane waves. And change the spacing of the fringes. So the Moiré pattern is giving the right position of the fringes. It's not giving the right intensity profile, but it's giving the right location of the fringes. Okay. I guess this is just the same. I just have, I'm going to use this pattern a few times. These are just 20 waves of tilt across a radius here. And then again, if I change the angle between the two, I'll change the angle, the spacing of the fringes. Okay, so now what we're going to do is that we have two patterns here where each one is 20 waves of tilt and 4 waves of defocus. So if I put them together, I see straight fringes. They're rotated, and so I have a little tilt left, so I see my fringes. And, oops. And so if I change the angle between them, I can change the spacing of the fringes. Now that's maybe not too exciting, but let's now go in here and let me rotate one of these, flip one of these patterns over. So that's going to change the sign. And so now what I have here is that instead of the pattern subtracting out, they're adding. And so I'm seeing my 4 waves of defocus plus another 4 waves of defocus, or 8. Should be 8 fringes of defocus there. Okay. Let me flip it back. Well, I don't know. Just get playing with this. I have too much fun. So I have 20 fringes of tilt, and then 20 fringes of tilt plus 4 fringes of defocus. And let me, again, just rotate that. So changing the angle. You can see how the tilt changes the fringes. Okay, this is 20 of tilt, and then 22 of tilt, 4 spherical minus 2 of focus. And so since one of these is 20 of tilt and the other is 22, well, I can't subtract out all the tilt. I have some left. I can change the angle of the tilt here. Again, by rotating. So this is 22 of tilt, 4 spherical minus 2 focus. So this would be like a shearing pattern. So this is spherical, and the shearing pattern gives something that looks like coma. Get the derivative. And put them right together. Of course, they cancel out. If I, oops. Rotate, I get tilt. And I could flip it and get the 4 spherical minus 2 focus twice. Okay. And so this is 20 of tilt, and then 5 of of coma. So on. 20 of tilt and another one 20 of tilt, 7 of astigmatism, minus 3.5 of focus. And one more down here. So 20 of tilt, well, 2 of these are the same. The 20 of tilt, 7 of astigmatism, minus 3.5 of focus, and they're flipped. And so you're seeing the sum. Now let me play with this one just a little bit. Let me get this out of the way. So this was astigmatism and focus. I had one up here that was just focus, I think. Ah, okay. Let's take this one here. And let's copy that. And let's come down here. Was that my last one? No, this was my last one. And now I'm going to paste this one. And so this now is taking one of focus and adding it to the one of astigmatism and focus. And we completely changed the shape here by essentially adding a different amount of defocus. Okay. So anyway, I put this up on the website last night. Oops. So you can download it, the PowerPoint presentation. And you can do this on a computer. You don't have to do it on the iPad, but it's kind of nice to do it on the iPad. It's easy to rotate and so on. So any questions on Moiré and see how it's related to interferometry, interference? And remember, it's a product of the two. The whole secret is you're not adding the two patterns, you're multiplying one by the other. And when you do this multiplication, that's where you get the difference term. And it's this difference term that gives you the low frequency. The high frequency, you just kind of ignore that and just think about the low frequency. Okay? Well, it's a little early to stop this class, but I think I'll stop at this point. And as I said this morning, I'm going to record 2 classes this afternoon. So we'll stop for 5 minutes or so, and then we'll start up again. Okay?